Hello. This Angel, they were doing the exam 1 for question 3. Question 3. So, start off here. Do part A. So part A says the electric dipole moment of a water molecule of H2O. So we know we have our oxygen, 2 hydrogen. H2O is at 6.13 times 10 to negative 30 Coulomb times meter. Place a water molecule in a uniform electric field of magnitude of 3.00 times 10 to the 5th newtons over Coulomb, with a dipole moment vector at an angle of 50 degrees in the direction of the field. Calculate the magnitude of the torque on the water molecule. So we have our water molecule right here, and we have an electric field going through it. Our field is at 3.00 10 to the 5th newtons over Coulomb, and we have a dipole moment, and we have our dipole moment of 6.13 times 10 to the negative 30th Coulomb times meter. Now, from here, we'll have a 50-degree angle. Pretty much, we're calculating the torque of its movement as this electrical field is going to go through it. So, we use the equation where torque is equal to movement times the field times sine of phi. So this is going to be simply plugging in our values right here of what we have, because we know that what we have right here is our dipole moment, 10 to the negative 3, which is our P, Coulomb times meter, multiplied by our charge that we have, which is our E, which is going to be 3.00 times 10 to the 5th newtons over Coulomb, multiplied by sine of 50 degrees. It's very simple what we have. So we're going to input this all in the calculator. We have 6.23 times 10 to the negative 30 times 3.00 10 and then times sine 50 degrees. So we input that all into the calculator, and this is what we get. So our torque for this movement right here, as this dipole is within the electric field, will be 1.4, run that over to 1.41 times 10 negative 24. And since we have Coulomb over here, they cancel out. This will be newtons times meter. And that will be our answer right there for part A. Let's move on to part B. Now part B is going to ask us to calculate the potential energy for the water molecule that we have right here in part A. Let's suppose that U is equal to 0. Now this time, there's a change in the fact that our movement vector is at an angle of 90 degrees instead from the direction of the field. So now we're moving 90 degrees from the field. So from here, we're going to use the equation for potential energy, where U is equal to negative P for the dipole moment times the electrical field cosine of P. Alright, so then again, we're just going to input our values of what we had previously. 6.13 times 10 to the negative 30 coulombs per meter, multiplied by our energy, 300 times 10 to the fifth newtons over coulomb multiplied by cosine of 90 degrees. And then from here, but it's actually not the right one because u is equal to 0 when it's at 90 degrees. So we have to reuse our 50 degree that we have over here. Which we were initially given. So I'm going to put this back. Where we have this point. Actually, best thing for me is I'm just going to move back up here and move all the way through until I get to sine. So we then switch this to cosine. And that right there is our answer, 1.18. Now, the main thing to forget is that there's a negative sign at the end of this. So our u equals to negative 1.18 times 10 to the negative 24 joules, since we are in our energy. All right, let's move down to part C. So part C now. The electric dipole is in a uniform electric field of magnitude of 8.50 times 10 to the fourth. So we have a field 8.50 times 10 to the fourth newtons over coulomb. And the charges in dipole separated by, so you have two charges here which are connected. Now this distance right here is 1.10 times 10 to the negative 10th meters. And the torque that's being applied on the dipole as they move through the field, torque is equal to 6.60 times 10 to the negative 20. Can't see it. Let me zoom this in. Negative 26 newtons times meter. All right, so for here, we have our torque, we have our field, and we have our meter. But we don't know everything yet. Now, since this is saying that charge, let me do this. Since these two are pretty much perpendicular to this movement here, at least as they move, they would be perpendicular to the electrical field. It'd be at 90 degrees, which means that it would just end up being 1. So torque would just be equal to PE. Since sine of 90 degrees is just 1, that means that it's just P. But P is also equal to Q times D. So we can use that because this is asking us to calculate the magnitude of the charges that make up the dipole. So we have to figure out charge. So we need our Q right here. So since that's P is equal to QD, that means that we can then put torque is equal to QD times E. And then let's move over the DE over to the other side. So now we have an equation for the charge where Q is equal to the torque divided by the distance times the field. We can then write this as Q is equal to a torque of 6.60 times 10 to the negative 26 newtons times meter all over our 1.10 times 10 to negative 10 meters multiplied by our electrical field of, was 8.5, yeah, 8.50 times 10 to the fourth newtons over coulomb. And there we are. So we're going to now input this calculators. 6 right there. So our fraction to be 6.60 times 10 to the negative 26 multiplied by 1.10 times 10 to the negative 10 multiplied by 8.50 times 10 to the fourth. So our answer for the charge, so Q is going to equal to 7.0 rounded over 5 to the 8 right here, 7.06 times 10 to the negative 21 coulomb. That's our answer for part C. That's our charge. Let me flip this over. And scroll down. And then let's go on to part D. Alright, so part D, saying you place a molecule in a uniform electric field, magnitude of 1.20 times 10 to the 5th newtons per coulomb. It requires 4.6 times 10 to the negative 20 joules of work to change the orientation of the molecule's dipole movement from parallel to the field to opposite of the field. Calculate the magnitude of the dipole movement. So, with this one right here, we have our dipole within an electrical field. Now, it requires a certain amount of energy of work to change the orientation from parallel to opposite the field. So right now, it's parallel to our field. So we can say that right now our sign is at 0. Especially when we're working with energy, because since this is with energy right here, we have to use our formula of U is equal to negative P electrical field cosine phi. Now cosine, when we're at 0, that means that we are parallel with what's going on right here. Now if we want to flip them to the other side, I'm going to use the energy of the, that's being used on it to flip it around. And then it will turn into just, so we have A and B here, and then B and A on the other side. So we have to flip them around. Now that would mean that our cosine, our angle would be on 180 degrees because we flipped around fully. We flipped over to the other parallel side. So for us to get this work to be accurate, that means that our work has to be equal to our energy at 180 minus our energy at 0 degrees. So that's going to look at, so pretty much negative P E cosine of 180 minus negative P E cosine of 0. Now, cosine 180 is 1, but it does mean it's negative 1. So this right here would then be negative 1 multiplied by negative PE, which comes out to be positive PE. And then when you're subtracting cosine 1, which would be 1, but subtracting negative means you're adding it. So then we have plus PE. So overall, we're then left with, when you equal these, to 2 PE. So if work is equal to 2 PE, and we have to figure out what is the dipole moment, which is our P, we then have to just divide by 2E on both sides. So P is equal to W over 2E. We'll just input what we have right here. So we've been given 4.6 times 10 to the negative 25 joules for work all over 2 multiplied by 1.20 times 10 to the 5th newtons over Coulomb. Right. So we're just going to take our calculator and we're just going to input those numbers together. We're going to say 4.6 times 10 to the negative 25 over 2 times, it was 1.20 times 10 to the 4th, actually 5th. Yeah. Oops. Here. That's right. Oops. There we go. That's parentheses correct. And there we are. So we're going to round this over. So our answer will then be 1.92 times 10 to the negative 30 Coulomb per meter. Joules could you write as newtons per meter? Cancel out. That's a Coulomb per meter. There we are. So that's for part D. It's part E and part F kind of connect together. Flip over to the next page. So now we're in part E. So with part E, it says the ionic molecule potassium bromide made up by a positive potassium ion. So we have a K plus over here. Charge of E plus E is equal to 1.6 times 10 to the negative 19 Coulomb, and a negative bromine ion. Bromine negative is a charge of E, negative E, so it's a negative 1.6 times 10 to the negative 19 Coulomb. So they're the same, just opposite. It has an electric dipole moment of 3.5 times 10 to the negative 29 Coulomb times meter. Calculate the distance between the two ions. We just have to calculate their distance of them together. So that means that we're just going to be taking P is equal to QD and just solving for D instead of P. So we're just going to flip this over, divide by Q. So D is equal to P over Q. Now these charges are the same, so we can use either of them. Value. So we're going to be equal to 1.6 times 10 to the negative 19. 18 Coulomb. And then we have the extra dipole moment 3.50 times 10 to the negative 29 Coulomb per meter. So we're just going to put this in a calculator. Easy. We just say 3.50 times 10 to the negative 29. Divided that by 1.60 times 10 to the negative 19. So then our answer right here is going to be 2.18. Round it over, it'll be 2.19 times 10 to the negative 10th meters. Coulomb cancels out. So then part F. Part F is then going to be saying how at a certain point along the x-axis, or along the axis that connects the ions, the electric field due to the KBr molecule has magnitude of 8.00 times 10 to the 4th newtons per Coulomb. How far from the center of the molecule is the point? So we have to figure out the distance. But this time we're figuring out the distance where it's greater than what it is currently. So we know that E is equal to a constant K over Q, absolute Q, R squared. Now R is also just equal to the distance between these two. So we can use this since we're given the field and we know the charge and we know a constant, we can then manipulate this to be able to figure this out. So if we know these right here, what we can do is we can say that Q is equal to P over D. Now, the reason we can do that then is because then we can say that E is equal to K constant over R squared, P over D. When you input it for Q, pretty much just puts our P up here and our D right here. Now, since R is pretty much just equal to D, we're going to say that this is all just X. There's all just the distance between these two. So since they're multiplied together, we'll just have X cubed. So from there, this is equal to this section right here. What we can then do is just manipulate this. So they're equal to each other. So we'll multiply X cubed on each side right here. So now we're at X cubed. E is equal to K P divided by E divided by E. So now X is equal to the cube root. So we'll cube root each side of K times the dipole moment times E. So we're just going to input all this together onto a calculator, or let's say the cube root of our K constant, which is around 8.98 times 10 to the 9th newtons times meters squared over coulomb squared times P 3.5 times 10 to the negative 29 coulomb to the meter, all divided by our 8.00 times 10 to the 4th newtons over coulomb. So that's the equation right there. All right, so we're going to have 8.988 times 10 to the negative fraction gets a 9 times 3.5 times 10 to the negative 29 divided by 8.00 times 10 to the 4th. Yeah. It's going to be 3.932. And then we're just going to take right here. So 3, put the answer in there. So our answer should then be 1.5. So 1.5. 1.58 times 10 to the negative 8 meters. And then there we are. So that will be our answer for part F.